Let's suppose we have a vector space V, and let's suppose that V equal to V1, Vn is a basis for V. Then we know that for every vector in V, this V can be written as a linear combination of these vectors. Then I can write it as alpha 1 V1 plus alpha n Vn. And we also know that these alpha 1 up to alpha n are unique because these vectors are linearly independent. We will be calling the representation of V with respect to these bases, and we're going to denote it like this: representation with respect to the basis B of the vector V to the vector alpha 1 alpha n. Notice that this space V can be a space of polynomial, of matrices, or it can be any vector space, but the representation is going to be a vector in either Cn or R to the n, depending if we are working in the complex numbers or the real numbers. Let's do some examples. Let's suppose that we have the V is the set of polynomials of degree 2 or less. And let's suppose that our base B are the polynomials 2 plus x minus x squared, 1 minus x, and 1 plus 3x. And let's take the element here, 12 plus 14x minus 2x squared. This is our vector V. And let's find the representation of, with respect to the basis B of this vector. Then essentially what we need to do is we need to find the weights. We need to write this vector as a linear combination of the bases, 2 plus x minus x squared plus alpha 2, 1 minus x plus alpha 3, 1 plus 3x. An observation is that this notation for the bases is not so good because it's written as a set, and you may think that the order doesn't matter, but we're going to assume that the order matters. Then let's continue here. Then in order to find the weights, we solve the system, and the system that we need to solve is the following. We can expand the right hand side, and we will get 2 alpha 1 plus 2 alpha 1x minus alpha 1x squared plus alpha 2 minus alpha 2x plus alpha 3 plus 3 alpha 3x, and we want this to be equal to this polynomial. Then the constant coefficient, which is 2 alpha 1 plus alpha 2 plus alpha 3 must be equal to 12. And the coefficient of x, which is 2 alpha 1 minus alpha 2 plus 3 alpha 3 must be equal to 14. And the coefficient of x squared, which is negative alpha 1, must be equal to negative 2. From here, we get that alpha 1 equal 2, and we can't do the math and check that alpha 2 is equal 3 and alpha 3 is equal to 5. Therefore, we get that the coordinates with respect to the basis V of this vector is the vector 2, 3, 5. I forgot to mention that this is called the representation of this vector with respect to these bases, but also these are called the coordinates. The coordinates of B with respect to the basis B, or the representation of B with respect to the basis B. Either name would be fine. Let's do another example. Let's suppose that we have the vector space R3 and we have the basis B equal to 1, 0, 1, 1, 1, 0, and 0, negative 1, 2. And let's take the vector V equal to 1, 4, negative 3. Then, in order to find the representation of this vector with respect to these bases, we need to write this vector as a linear combination of these three vectors, and the weights are going to give us this representation or the coordinates. Let's do that. We write alpha 1, 1, 0, 1 plus alpha 2, 1, 1, 0 plus alpha 3, 0, negative 1, 2 equal to 1, 4, negative 3. Then this is equivalent to the system alpha 1 plus alpha 2 equal 1, alpha 2 minus alpha 3 equal 4, and alpha 1 plus 2 alpha 3 equal negative 3. And we can check that the solution of this system by doing row reduction and everything is equal to alpha 1 equal negative 3, alpha 2 equal 4, and alpha 3 equal 0. We can check this equation is true. 4 minus 0 is 4, and negative 3 plus 4 is 1. That means that the coordinates with respect to this basis B of this vector V is the vector negative 3, 4, 0. If we consider another basis for R3, let's consider gamma equal to 1, 0, 0, 1, 1, 0, and 1, 1, 1. Then the representation with respect to this basis of this vector would be the solution of this system. Alpha 1, 1, 0, 0 plus alpha 2, 1, 1, 0 plus alpha 3, 1, 1, 1 equal to 1, 4, negative 3. And then we set up the system, which is alpha 1 plus alpha 2 plus alpha 3 equal 1, alpha 2 plus alpha 3 equal 4, and alpha 3 equal negative 3. That means that alpha 3 is negative 3, alpha 2 should be equal to 7, and alpha 1 should be equal to, this is 7 minus 3 is 4, it would be also equal to negative 3. That means that the coordinates with respect to this basis of this vector are negative 3, 7, negative 3.